Okay, good morning, everyone. Welcome to the BRO seminar series. I'm honored to introduce our today's speaker, Dr. Rolfe Mandel from the Kansas Geological Survey, KGS. Dr. Mandel received a BA in geography from the University of Texas, Austin, an MA in geography from the University of Kansas, and a PhD in spatial studies from KU with a focus on quaternary research. Currently, he is a director of the Kansas Geological Survey, or KGS, and the State Geologist of Kansas. He also serves as senior scientist and executive director of the Odyssey Geoarchaeology Research Program at the KGS and is a university distinguished professor. Dr. Mandel has spent most of his career studying air surface processes, especially the evolution of stream valleys and soil formation. Much of his recent research has involved the use of geoscientific methods to search for the earliest evidence of humans in the central Great Plains, Midwest, Big Bend region of Texas, and the Canadian Yukon. Dr. Mandel has received many awards and distinctions for his research and teaching at the University of Kansas. He has held national and international leadership positions, including president of the American Quaternary Association and chair of the National Academy of Science U.S. National Committee for Quaternary Research. He has published extensively with more than 100 peer-reviewed journal articles, book chapters, and technical reports. In 2014, he was named University Distinguished Professor. So without further ado, I'll hand it over to Dr. Mandel to start.
Okay, thank you, Sahar. Appreciate the nice introduction. Michael, thank you for inviting me. It's a real honor for me to come here. As Sahar mentioned, I got my bachelor's degree almost 50 years ago, which kind of dates me, but coming back to UT and coming back to the Bureau is just always a delight for me, a real privilege. So thanks for having me. In fact, this is the first lecture in person I've given since the pandemic. So it's nice to actually come back and see some people rather than staring entirely into a screen giving a lecture. So I'm really delighted about that. So with my job, I wear a lot of hats. I'm director of the Geological Survey. I direct the Odyssey Geoarchaeological Research Program at KU, which is an endowed program that provides resources for searching for the earliest evidence of people in the New World. Particularly, my focus is the mid-continent, though I go outside of it as well. But I get geoscientists engaged in archaeological research. I am a faculty member of the Department of Anthropology. Well, I'm not an anthropologist. I teach geoarchaeology in that department. So what really got me back into the Big Bend region a few years ago was that search for the early archaeological records that was supported by my Odyssey research. But I thought I might as well begin at the beginning. So when I grew up in San Antonio and went to Alamo Heights High School, which is a very progressive school. And they actually brought in a professor from Trinity University to teach college level, introductory level geology course. And I took that course and I belonged, as you can see, to the geology club. This was in 1970. And he was brave enough to take this class on a field trip over a long weekend to Big Bend National Park, okay? And so at the end of that field trip, so this was 1970, I decided that's what I wanted to do in my career was to go into geoscience. And as director of the Geological Survey, when I do outreach, I often mention this to students when I go to high schools. I say, you know, something might capture your attention in high school, and that actually might be your career. So I've really come full circle, because in the 90s, I became a consultant for the National Park Service in Big Bend doing research on the Quaternary of Big Bend. And now, again, I'm back in Big Bend. So this is my roots. You can see the arrow pointing to my head. I had a lot more hair and it wasn't nearly as gray back then. So anyway, I thought I would share that with you. So this is going to be a little bit of a circuitous route to get to where I want to talk about Big Bend. So I want to talk a little bit about lithostratigraphy, and I put this slide up just to show, because I'll be talking about this in detail. What is a lithostratigraphic unit? And I note here it's a body of sediment that is distinguished and delimited on the basis of lithic characteristics and stratigraphic position. Litho units are defined by observable rock and sediment characteristics such as color, texture, organic matter content, and carbonate morphology. In other words, a lot of these properties you can actually witness in the field. You can see color, you can see carbonate morphology. You can detect the texture of the material. I note here the boundaries of litho units may be time transgressive, but some may be approximately synchronous. However, time plays no part in determining the boundaries of any unit. So depending upon where you are in a drainage network, if you're, say, in small order streams, the age of that litho unit will be synchronous, but as you move into a larger higher order portion of the drainage basin, it's likely to become progressively older. So it's time transgressive. Hence it's not defined on basis of age, but there are bounding ages if you know where you are in the drainage network. I note here that non-continuous floodplain sedimentation through time may result in recognizable lithologic contrast between alluvia of different age. These contrasts may develop from the effects of progressive in situ weather. So soil formation is going to modify the litho units, changes in sediment source area, and or changes in the dominant fluvial processes, lateral accretion versus vertical accretion. I note here that lithostratigraphic units they're directly observable in the field as field units. They may allow temporal correlation of the sediments in one area with those in another, places the sediments in a systematic sequence, and indicates their relative position with respect to Earth history as a whole. And then I note these useful applications that can be used to interpret the temporal and spatial patterns of archaeological records in a region. Lithostratigraphy can also be used to develop predictive models for buried cultural resources. Litho units have been used for groundwater hydrology, water quality, movement of water, storage of water, and soil and sediment erodibility. So my point here, it's kind of a preemptive strike. If you're wondering, why am I talking about lithostratigraphy in the Big Bend region? There's actually a good reason. There's actually multiple reasons. So I've shown you here. Of course, with what I'm doing in the Big Bend region now, the application of lithostratigraphy to understanding the archaeological record it becomes a very, very powerful tool, as I hope you'll understand by the time I'm through with this lecture. Okay, I don't expect you to read all this, but what I thought I would do, because I've spent at least 40 years looking at lithostratigraphy in the Eastern Plains and Midwest, and specifically looking at the DeForest Formation. My good friend and colleague Art Bettis and I have roamed all over Iowa, South Dakota, Eastern Nebraska, Eastern Kansas, Missouri, basically looking at the DeForest Formation. It was originally defined by Daniels et al. Daniels, he is really a pedologist, and some of you may be familiar with his work on looking at soils, particularly in Iowa. He's one of the big guns in pedology, and did a lot of work on fragipans. He's really well known for that. But he created the DeForest Formation. He recognized this lithostratigraphic unit and identified various members of it. And Art Bettis and I then basically expanded the DeForest Formation out of Iowa into the adjacent states. And I note here the DeForest Formation consists of 8 formal members, 5 of which occur outside the boundaries of the Des Moines Lobe. And I've got these different members listed. And I'm just going to quickly show you what these different members of the DeForest Formation look like. And what's kind of scary is that when I got into the Big Bend region, started looking at the Holocene alluvial fills, they look a lot like these different members in the DeForest Formation. I'm not going to be bold enough to take the DeForest Formation and move it into Texas, into Southwest Texas, because it does differ particularly in carbonate morphology. We don't have the carbonates like you see in these different members I'm going to talk about today in Big Bend that we see in the DeForest Formation. But there's some remarkably striking similarities And I think there's links with climate that's driving those similarities, particularly bioclimate. So just as an example, this shows the Gundar member of the deforest formation. I've just listed some of the characteristics, but when you walk up to a stratigraphic section, if you see this fairly well oxidized sediment, typically has a pretty well developed soil at the top with an argillic, a BT horizon. Once you see the Gundar member, it looks the same everywhere throughout the eastern plains and Midwest. This is a great example of what it looks like. So very distinguishable based on its lithologic characteristics. I list here the Camp Creek member and the Roberts Creek member. You can see all the different characteristics. And on the left, you can see the Camp Creek member is about, almost 2 meters thick. And what's distinguished, makes it really stand out, is it's stratified. This is what we commonly refer to as post-settlement alluvium. In other words, when the Euro-Americans came into the region, started plowing the land, cutting down timber, all the sediment poured into the drainage basins very quickly. And if you have any doubts about the age of it, if you look at the bottom, and I'll point this out, that is a beer can midden. And we were actually able to date the cans because they're tin, dating back to about the 1950s. So someone was having a party by the side of the stream. But notice the distinct stratification, surface soils, AC profile. It's a really weakly developed soil, as you would expect, because this is less than 100 years old. And so it's sitting on top of the Roberts Creek member, which is this really dark, humic, organic rich A horizon, which is, by the way, sitting on top of the Gundar, which is somewhat reduced in this setting. On this slide, you see the stratified sediment. And that's the Camp Creek member. Notice the plastic jug sticking out right there. So it's very young. It's post-settlement alluvium. But over the Roberts Creek member, this very dark cumulic A horizon. What I mean by cumulic is that basically sedimentation was very slow and soil development was keeping up with it. Organic matter was accumulating. So the real diagnostic characteristic of the Roberts Creek member is this over-thickened A horizon. And you're going to actually see a very similar looking soil in Big Bend when I take you there. And for that matter, you're going to see a very similar unit of stratified sediment that pretty much blankets the different members in the Big Bend region. The Honey Creek member, it's a late Holocene unit. It's this very gray sediment. There's lots of cross-trough bedding, trough cross bedding in the bottom of it. Really weak soil development, unlike the Gundar, not very well oxidized. Again, once you see the Honey Creek member, you know that's the Honey Creek member. Very distinguished characteristics, lithic characteristics. The Corrington member, I note here, it's restricted to alluvial fans. Multiple upward finding sequences that are capped by weakly developed soils, except for the surface soil, which typically has a BT horizon, as an argillic horizon. And these fans tend to date from early to middle Holocene. You see a whole sequence of radiocarbon dates. That's very typical of the Corrington member. So again, once you've seen the Corrington member, and you can see here this alluvial fan, there's the fan head trench. It's pretty much the same from fan to fan, both in terms of its lithologic characteristics and also as well as its age. And just to show you one example of how this is very powerful in the field in terms of distinguishing these different litho units, the different members in particular. This is the Claude archaeological site. It's only about 20 miles west of my home in eastern Kansas along Mill Creek. And you can see there's a low terrace, there's a flood chute right here, and then coming up onto a high terrace. And we're going to zoom in on this section. There's that flood chute that's in the middle, and we'll zoom in a little bit more. So when you look at this illustration or this photo, the Gundar stands out as this oxidized fill. The Roberts Creek member, this big, thick cumulic A horizon, where this fine-grained organic rich sediment accumulated in an abandoned flood chute that's very distinguishable. And on the right side, we have Honey Creek. And by the way, there's archaeology in all three of those members. And not surprisingly, the cultural deposits in the Gundar member, or the basal ones, date to about 10,300 years before present. the Roberts Creek, which is a late Holocene unit. There's lots of what we call plains woodland that's about 1,500 years old. And in the Honey Creek member, there are cultural deposits that are anywhere from 300 to 400 years old to about 900 years old. But the main point I want to make is that you can walk up to these sections, look at these lithologic characteristics, and call out what these different members are. And if you know where you are in the drainage basin, if you're high, middle, or low part of it, you can pretty much, before you even have radiocarbon dates, you can actually assess what the likelihood of the age of these different cultural deposits are. In the Eastern Plains, also another luxury for archaeologists is if you can map out the different members of the deforest formation as shown here. This is in Fox Creek Valley. If they're at the surface, and this is an important point because this doesn't apply very well to Big Bend, but in this part of the world where these members actually form fills that are at the surface, if you map these different members, you can go from this to this, where you can then determine the potential for buried prehistoric culture deposits, the red being very high, the dark green being very none, which means that this is where the Camp Creek members at the surface and below, for that matter. So again, it becomes a very powerful tool for archaeological research, especially for doing archaeological surveys. Yeah, as I mentioned, it has other applications. For example, Tony Lazelle, who was actually started his PhD here at the University of Texas, and eventually came up to Kansas to complete it, and is now a scientist at the Kansas Geological Survey. He and I were looking at the erodibility of these different members, and we published this paper in Geomorphology that assesses the erodibility of these Holocene litho units that comprise stream banks. And this is really important in Kansas because a lot of the reservoirs are filling up with sediment. And so people involved in that research said, is there any way you can tell us, based on what you see in the streams in terms of these different members that are exposed along stream banks, are some contributing more sediment than others? And so should we target some of those areas for bank stabilization? So this is a real world application of lithostratigraphy. Okay, so now it's time for me to jump into Big Bend. So I've kind of laid out the framework of what I really want to talk about. And I want to begin, as you saw in my title, walking in the footprints of Kirk, Bryan, and Claude Albritton. So I'd have to say that the Kirk Bryan is really kind of a hero of mine and has been for a long time. He was at Harvard as a professor in the geology department, and spent a fair amount of time in Texas during the late 1930s and 1940s, particularly in the Big Bend region. But as a student, I was always fascinated in his application of geoscience to archaeology. He was a geoarchaeologist. And so it's funny, I teach a geoarchaeology lecture course with undergraduates and graduate students. And I was telling them, I was getting ready to show them this picture. And I said, Kirk Bryan is really my hero. He's like, I idoled him. And one of the undergraduate students said, well, yeah, I thought I saw him on American Idol. And I said, no, he's been dead a long time. And I showed him this picture, but he really, I would say, had a great influence on my career. When people ask me who really kind of helped shape your career, even though he was dead long before I got started, but reading his literature really encouraged me to go the direction I went. Claude Albritton was a professor at Southern Methodist University, and I actually got to know him slightly before he died when I was a student, and a very fine gentleman and a great scientist. And so J. Charles Kelly, who was an archaeologist in Texas, he was a graduate student of Kirk Bryan's, and I got to know J. Charles Kelly as well, and he told me a story about how he actually got Kirk Bryan down to Texas, talked him into coming down to the Big Bend region and study the soils, the stratigraphy. And Kirk Bryan then got Claude Albritton, because they were good friends, out to work with him. And so the two of them did quite a bit of collaboration. You look at their literature, a lot of it, even though the term lithostratigraphy is not used, they were looking at lithic characteristics of these valley fills in the Big Bend region, the Holocene fills. And so they were trailblazers in terms of looking at, and also applying geochronology, although they had no radiocarbon, that was not available then, but based on soil evidence, they were able to infer ages of fills and soils. And it's really quite, I'm going to come back to that. But anyway, both of these men really had a great influence on me and really got me excited about working in the Big Bend region. This particular article by Bryan and Albritton, really, it stands out. I make my students read this. Soil phenomena as evidence of climatic changes. And a lot of what you see in this article comes out of their work in the Big Bend region, the Davis Mountain area, as well as Calamity Creek, which I'm going to talk about today. So it's a great example of the early work where geologists, in this case, were looking at soils evidence and inferring what was the climate like during those periods of soil development. So it's just a great benchmark paper. This volume by J. Charles Kelly and Campbell Lemur, 1940, is just packed full of information about the soil stratigraphy and these different, what they call formations in the Big Bend region, and really pulled in a lot of Kirk, Bryan and Claude Albritton's work. And so, great example of archaeologists using geoscience to frame the archaeological record of a region. And so again, this is a really important work in terms of early work of looking at the application of geoscience to archaeology in the Big Bend region. This is a map, and it may be difficult to see a lot of the detail, but you see lots of circles scattered around. Those were localities where Kirk, Bryan and Claude Albritton worked. One in particular, where the arrow is pointing, this is Calamity Creek, here's Elephant Mountain. They spent a lot of time along Calamity Creek looking at stratigraphic sections. And these are some of the photos, black and whites, that are in the book. And what stands out, you see these really thick A horizons like this one and that one. And this lighter sediment above it. That's the lighter sediment above it is the historic sediment, mantling this really thick humic A horizon. And what captured their attention was they would often see archaeological deposits like this hearth, particularly associated with the buried soils, which makes sense because the buried soils represent former stable or at least quasi-stable landscapes in terms of the humic soils that people would have occupied. So they were really interested in sorting out the soil stratigraphy of the Big Bend region for that reason. So this is what they saw in color. This is Calamity Creek along the base of this cut bank, and you can see this very prominent buried soil at the top of it. This is Elephant Mountain in the background. You notice the vegetation today; it's pretty much a desert shrub, a lot of creosote, a lot of mesquite, a lot of cactus. If you could go back in time before this area was grazed, and that began in the 1600s, it would have looked a lot different. It would have been primarily a C4 grassland with very little shrub. As the area was overgrazed, basically the mesquite and the creosote are like shrubby, woody weeds that came and invaded. For that matter, even the cactus really invaded. And so this is not a very good analog, what you're seeing here, for what it likely looked like in the past before the area was settled. But it certainly looked like this when Kirk, Bryan and Claude Albritton went out there. I'm going to zoom in on that section I just showed you. For scale, this is a 20-foot ladder extended. So there's no shortage of big, thick sections out there. And you can notice just from this photograph, there's a really light zone up here. That's what they call the Kokemot formation. There's this big, thick humic A horizon over this grayer, sort of a light brown to light gray material. And there's this reddish buried paleosol right here. This they lumped all together into the Calamity formation, and this was from the Neville formation from here down. We look at it up close, that section. And so there's the Kokemot. This is that historic sediment, younger than, typically, a lot of it's younger than 300 years old. That's the Calamity formation. And this is the Neville formation. And so they took this stratigraphy and pretty much expanded it across the entire Big Bend region using the terminology that you see here, these three different formations. They've got lots of diagrams in that 1940 bulletin I showed you earlier. There's the Kokemot. They call that dark soil at the top, they just refer to it as a humic zone. It's clearly an A horizon. They'd see other buried A horizons within the Calamity formation. And there's the Neville. You can see it's a real wavy boundary. There's an erosional disconformity that separates the Neville from the Calamity. But the stratigraphy, it would come and go. In other words, in terms of the number of different formations, you see all three of them in this one. In this one, you see there's the Kokemot at top, there's that humic zone, and then it just stratified. There's another humic zone here, and you don't see the Neville. So they're not laterally continuous. They're in many places, for that matter, the Neville has been totally cut out by erosion. Sometimes the Calamity is very thin. The Kokemot, I would say, is pretty much ubiquitous across the valley floors, except when you get right up to the channels where there's been a lot of erosion, and sometimes it too has even been eroded off in historic times. So what I note here, these are kind of the takeaways of the work that Bryan and Albritton did. And there are more than this, but I just thought I'd hit on some of the major ones. So based on the lithologic characteristics, valley fills in the Big Bend region consist of what they call three formations: the Kokemot, Calamity, and Neville. The Neville formation mostly consists of this reddish brown. That's a real key. When you walk up to a section, you see this reddish brown sediment, you know that you're in the Neville. And they assumed that it degraded during the late Pleistocene. Now again, there was no radiocarbon dating then, but what they saw were mammoth remains. They knew there was Pleistocene fauna associated with it. So they said that it's at least late Pleistocene and perhaps extends into the early Holocene. Paleosols developed this unit, have many calcium carbonate films, threads, and nodules. What we would call today would be stage 2 or stage 2+ carbonate morphology. The matrix is somewhat whitened, as you'll see when I'll show you some other slides of it. So that's a real distinguishing characteristic of it, is accumulation of calcium carbonate. In other words, another lithologic or lithic characteristic. And as I mentioned, there's an erosional disconformity that separates the Neville from the Calamity. The Calamity formation mostly consists of brown and pale brown silty and sandy alluvium that degraded during the Holocene. They just figured that it pretty much spanned much of the Holocene. Aggradation was punctuated by brief episodes of soil formation. So they would see these very weakly developed buried soils within the Calamity. And in fact, in that American Journal of Science article, they used a term I'd never heard before. They called them precocious soils. I'm trying to think how a soil could be precocious, but I would say what they were really referring to is they were poorly developed, early stages of development. Incipient might have been a better choice of words. They noted that cultural deposits are often buried in the Calamity formation. So as I showed you earlier, they would often see that there were features, archaeological features, artifacts, and that an erosional disconformity separates the Calamity from the Kokemot formation. See if I kind of get rid of this. Okay, is that better? Well, that's fine. Okay, and then finally, the Kokemot formation mostly consists of stratified silty, sandy, and gravelly alluvium that degraded soon before what they thought, soon before AD 1200 and continued to accumulate until AD 1880. They gave a specific date, and that's based on oral histories from landowners. Entrenchment occurred after AD 1880. So the stream channel was way up high in those, if you think about that section I showed you, the stream channel was way up there because there are actually lateral accretion deposits sitting on top of what they called the Calamity. So entrenchment, deep entrenchment occurred. And of course, that's probably, I think it's safe to say, is related to land use when the landscape became overgrazed. that would dramatically accelerate erosion. It might have been a complex geomorphic response because a lot of sediment had piled up and it just is ready for incision to occur, and that land use, increased runoff, probably pushed it over that threshold. So you see deep incision throughout the whole region in these valleys, often 10, 15 meters, and sometimes more of incision. Okay, there we go. There we go, got it. Okay, so I note, while they did great work, I'm not questioning that, there is a problem with referring to the Kokemot, Calamity, and Neville as formations. Now, the North American Stratigraphic Code did not exist when they were working out there. And so I note that today, according to the North American Stratigraphic Code, formations must be contiguous, mappable units. Also, I note here that there's an erosional discontinuity between the Calamity and the thick humic zone above it. So I'm not really sure why they didn't split that out in another unit. But the bottom line here is you really can't refer to these as formations because you cannot map them across the valleys, either cross them up and down the valleys. The Kokemot maybe, but the Calamity and Neville are in a buried context. And so if you're putting together, like for state map, if you're putting together using a 7.5 minute quad, there's no way to map the Calamity or the Neville. And so, if you combine them into a unit, then you could map that unit, but separately, it just doesn't work. So the objectives of my research is to refine the Holocene and terminal Pleistocene lithostratigraphy defined by Bryan and Albritton in these stream valleys, determine the numerical chronology of the valley fills, and reconstruct bioclimatic change for the period of record. I'm gonna talk. I don't know why it's gave them all ones, but it did. there should be three. Anyway, I'm going to talk mainly about the first two and a little bit about the last one. There's just not going to be a whole lot of time to go into the bioclimatic change story, but I'm going to touch on it. Okay, so the areas that I've been looking at in the Big Bend region here, Brewster County, Presidio County, make up a big chunk of the landscape in the Big Bend region. And this is the Calamity Creek study area. This is the O2 study area, O2 Ranch. I'm not going to really say much about San Esteban. It's a rock shelter we've been working on, but I will make a comment about that at the very end. So I'm going to begin on the O2 Ranch. It's an immense ranch. It's one of the largest ranches in Texas. I think it's probably in the top 5. It's about 45 miles across. And this is Terlingua Creek, which is the high order stream in this area. And this is Duff Creek, which also is referred to as the ditch. Everybody refers to it as the ditch. And when you see pictures of this, you'll understand why. And you'll see all these sections numbered here. These are sections I've looked at. There's a couple sections, one here, and section 7 is right above it on Terlingua Creek. There's the GLD site. I'm going to talk a little bit about that. So I'm going to give you a tour of this in a minute. So this is probably one of the most important photos that defines what I'm talking about here. So what I say here is step 1, create a new lithostratigraphic unit. Because as I said, using those formations that Bryan and Albritton defined just doesn't work. So what I've done is I've put all of these, what they called formations, into the Likes formation. The Likes bought the O2 Ranch in 1940, and they're still part of the corporation that owns that ranch. And a lot of the work I'm doing is on the O2 Ranch. So I thought it was appropriate. And you often see formations named after ranches, big landowners in that part of the world. But the reason I say this is a really important photograph is you can really see, first of all, the boundaries of what I'm going to show you in a minute are members. Really nice example of what they call the Kokemot. But the thing I really want to point out is the absolute razor sharp boundary between this cumulic soil, that really dark cumulic A horizon, which they referred to as the Humic Zone. The boundary is just razor sharp between it and what they call the calamity. And there's another sharp boundary here between the calamity and the Neville, okay? So when I saw this in particular, this is a separate depositional unit that's not, this soil is not genetically related to what's below it, okay? So important point, because what I did then was in the likes, step 2 is to define the different members. And so I used their terminology. I changed their formations to members, and I added a member. This is what I'm calling the Terlingua Creek member. So I've slightly modified the terminology, the nomenclature they've used, and added one member to it. So this is collectively, this is all now the likes formation. So it's a lithostratigraphic unit with different members that are defined on the basis of their lithic properties. So I'm going to just show you the consistency. Remember I said lithostratigraphic units, you have to see consistent patterns in lithology. And just to show you examples of this, so in this case, the Terlingua Creek member is actually at the top. There might be just a few centimeters of the Kokemot member on top of it. Most of it's been eroded next to the stream channel. Here's the calamity member. And then you see right here, it starts getting red. It's rubified. That's the Neville member. And Bryan Schroeder, who's the director of the Big Bend, the Center for Big Bend Studies, is pointing to charcoal next to a hearth that's buried in the Neville member. And that's pretty common. You see particularly late Paleo-Indian cultural features buried in the Neville, very common. This is along Duff Creek. So we're going from Terlingua to Duff Creek. And I put abbreviations for these different members: the Kokemot, the Terlingua, the calamity, and the Neville member. And you can see the changes in color. And what's striking here is that the Terlingua is actually filling, you can see it filling what was probably an arroyo channel, and then it thins as a flood drape and then fills another channel here. This is strikingly similar to what we see with the Roberts Creek member in the Eastern Plains in Midwest. It typically fills abandoned channels like that flood chute I showed you. It's really like a soil sediment. Again, it's a cumulic soil that are graded both in topographic lows in the former floodplain, and there's an erosional unconformity that separates it from the calamity below it. So it's, again, these are not genetically, that soil is not genetically related to what's below it. And then it forms a flood drape, and then here another fill, so a channel fill. Again, just another example. You can see here's the Kokemot, stratified, very young. The Terlingua Creek member, this big, thick cumulic soil. Calamity member, this light colored brownish to gray, and this redder Neville member below it. This is at the lower end of Duff Creek. Now you can see why they call it the Big Ditch. So there's Bryan for scale. So it's an enormous section, which I was trying to figure out how I was going to describe it. I'm going to go back to it and figure that out later. But this is a section I do want to get back to. Although in this section, just at quick glance, I think all of this is the calamity member. From here on down, you can see there's the Terlingua, the dark cumulic A, and there's also the Kokemot member at top. And getting down on the section, you can see there's the Terlingua member, there's a Kokemot at the top, and this is all calamity. Now, I'm not going to say it's impossible for the Neville to occur below where she's standing. It's possible. But at least in what we see here, this is all typical calamity. And you can see must be one of their precocious paleosol, precocious soils. It's a pretty weakly developed soil that's within the calamity. And sometimes you'll see one or two, sometimes three soils like this up and down the sections. Okay, so, oops. I'm going to take you, so we were mostly up in the northern part of this box. I'm going to take you a little further south to the O2 Ranch. The Genevieve likes Duncan. I just refer to it as everybody else as the GLD site. Here's Terlingua Creek. Here's the site. Here's Davenport Draw to the east. So it's on this low divide between the two. It's basically a terrace fill. And so the Center for Big Bend Studies has been working out there for the past decade or more, excavating, because as you'll see, they have found lots of archaeological deposits that date particularly to the late Paleo-Indian period and also to the early Archaic and some later. They put in a whole bunch of trenches. You can see here, there's a big trench here, and they put in a big block excavation, another series of trenches. And so a number of people have worked out here. I'm going to show you, this is what it looks like in the excavation, that excavation block. So Andy Claude, who used to be the director of the Center for Big Bend Studies, spent a lot of time out here. And Charles Frederick has done some of the geomorph out in this area at the site. Arlene Rosen, who's here at the University of Texas in the anthropology department, looked at some of the phytoliths. And so it has a long history, relatively long, of research at this site. And what drove a lot of this has been the discovery of these earth ovens like this one in Plainview. And in fact, the earliest earth oven documented in North America was documented at that site. It dates back to nearly 11,000 years ago, which makes it the earliest earth oven in North America. And they were using these earth ovens to process food, root foods particularly. There's a whole variety of plants that are edible as long as you heat them. So they put them in these earth ovens and cook them. And so a lot of information has come out of this. I don't really have time to go into the archaeological record, other than to say it's a pretty impressive record. People like this spot and revisited it through time. And the way I operate is I often look at sites that have been frequently occupied through time, and I come to those sites and I go deeper, because something drew people to these localities, and it makes me wonder, could there be an earlier record that's much deeper? And so last summer, I got the Odyssey team out there, and they excavated a 4x4 meter block, as you can see here, all the way down to the bottom into gravels. And there you see these members, the Kokemot, the Terlingua, the Calamity, and there's the Neville. And you can see some rocks. That's part of an earth oven right there. This is where they stopped excavation. So we just went down lower to see, is there something older at greater depth? And this is what I discovered. This is that late Paleo-Indian component. This is where those earth ovens are commonly found. There are two buried soils beneath it, what I call soil 6 and soil 7 right here, which have fairly decent carbonate morphology, stage 2. You can see the carbonate threads, and then it becomes stratified, and then at the bottom, it's all sitting on sand and gravel, these lateral accretion deposits. We have an OSL date that's just preliminary right now that Tammy Rittenauer, actually 2 dates. She won't swear by them, she's still processing it, but she estimates they're going to come in around close to 15,000 years ago. So that we're at about 15,000 at the bottom of the section with these. So there was rapid sedimentation, slowed down, soil 6 developed, or soil 7 developed, then soil 6 after another period of deposition. It's truncated by these gravels, then soil 5 above it that has the late Paleo-Indian record. What's intriguing is just a few meters away, they had excavated a trench in the bottom of that arroyo, at the bottom of this cut bank. And here's that late Paleo-Indian surface in the Neville. And so they went down, and there's soil 6 and soil 7 that I just showed you in our 4x4. And there's charcoal here. They just found this chunk of charcoal that dates to 10,730. So that puts us into Clovis time. on the more recent end of Clovis. But when you just find a piece of charcoal, it's is this archaeological? In other words, is it, or is it just a piece of charcoal that got washed in? What's the context of it? But it's intriguing that it's sitting in this buried soil, 7, a buried landscape that people could have occupied. That in itself was intriguing. But what was more intriguing is what we discovered right after we left from the summer in back dirt from the trench that I just showed you, in that area where it was excavated, in back dirt of a trench, due to the rain, they had missed a Clovis point that was laying there. And this is actually what we call a preform. In other words, they were making a Clovis point. And so there's likely a Clovis camp there. This is not a point they'd been throwing a projectile at a mammoth. They were manufacturing Clovis points. So it suggests that there's a Clovis camp. So we've got an artifact. We've got a date that dates to Clovis. And so it intrigues us even more to the point now, this next summer, we're going to go back and put in a block excavation over that area I just showed you, where the charcoal and the point we know came out. We know the point came out deep, probably from that soil, is my guess, because of where it was on the pile. It was the last scoop they took out. So it's just really exciting that there could be a Clovis component. And a stratified Clovis site has never been discovered in the Big Bend region. In fact, they're pretty rare in that general area of Texas and even beyond. In Kansas, we have 2 sites that are stratified Clovis sites. So there's our target. We got, and this again, we've got a buried soil in the Neville member, so that makes that a target. Not just here, but think about this. If we start tracing that buried soil in the Neville up and down the drainages, maybe there are other, we're calling this at least a potential Clovis site, but this is a target to focus your search. So I'm going to show you a little bit of data. On the left is this is a composite of that wall I showed you with the different members outlined, and then going down into our excavation block. And so there's the Kokemot member, nice stratified sediment on top, very young. The Terlingua member, this over thickened A horizon. And you look at the radiocarbon dates. Now these are all determined on soil. The black squares are soil organic matter that was dated. Although it tends to work pretty well in dating soils because it's calcareous sediment. That tends to limit the movement of clay and organic matter attached to it. So 800, so we know it was buried sometime after 800, about 1500, 3100, and then this is charcoal from a feature. We're jumping to 6000. So there's a unconformity, a disconformity that separates the calamity from the Terlingua. We're really jumping in time. We come down into the Neville and a whole cluster of dates from 8440 to 9410. And again, these are dates on charcoal from archaeological features. Here's that date of 10730 from that one chunk of charcoal. And like I said, we've got dates on OSL that are probably going to come in around 15 or so at the bottom. On the right, you can see the texture of the sediments. It's actually pretty darn silty throughout the whole profile. There's some excursions here of sand, greater increases in sand, not particularly clay. But what's an interesting note here is that the top of the Neville tends to be really silty. And Bryan and Albritton noted that too. And they looked at the color, that reddish color, and they made the observation that a lot of the rock shelters, you see loess that's piled up in the back of the rock shelters that is sort of reddish. And so they said, this is likely the source of the Aeolian sediment that's stored in the rock shelter. And lo and behold, in the San Esteban rock shelter we're working on to the west, about 30 miles, 30, 40 miles west of here, there's an incredible loess sequence. And a lot of it at the bottom is reddish brown, and it dates to the Neville. Now, that would have been the floodplain. That would have been the source. And so it'll be an opportunity for us to come back and do fingerprinting of the mineralogy of the Neville as it relates to the loess and the rock shelters. But I think that this is another example where Bryan and Albritton got it right. They had it figured out. A quick comment, I'm not going to go into a long lecture on isotope geochemistry, other than to point out that you have C3 and C4 plants. The C4 are the warm season grasses that are common in the Big Bend region, dominate the plant community. C3, there's a lot today with the woody shrubs, but they weren't around before much, at least not much, before the area was heavily grazed that altered that landscape. And we know that as the organic matter from these plants falls to the ground, gets incorporated with the soils as soil organic matter, if you go and measure the delta 13 values, you can look at how much C3, in other words, values that are in that -26 to -22 point to woody vegetation or cool season grasses, though there aren't many now in the community of cool season grasses, versus you look at values of -12 to -16, that's a strong C4 signal, warm season grasses, that you can through time then say something about how the vegetation community changed, which was driven by climate. So then you use that as a proxy for climate change for the period of record. So stable carbon isotope analysis of soil organic matter can be a very powerful tool to tell you something about temperature based on looking at C3 versus C4 values in the delta 13. So in this diagram, two things I'll note before I plunge into talking about the delta 13. This is calcium carbonate equivalent, and it's not particularly high in certainly not in the Kokemot. The Terlingua increases slightly. There's a little bump in the Calamity, but it's generally less than 10. But as soon as we get down into the Neville and into that paleosol or paleosols, multiple paleosols, we see that the calcium carbonate equivalency increases dramatically. You can see a real big peak here that's associated with this buried Paleo-Indian age landscape. So, not surprising because we're looking at pretty much stage 2 to stage 2+ carbonate morphology, but significantly higher up to greater than 15 versus 5, throughout most of this. Organic carbon content, it's pretty high at the top of that Terlingua member, decreases with depth, although still is pretty high. 0.5% is still pretty high. And then it really drops off in the Calamity, bumps up a little bit as we get into those buried soils at the top of the Neville, and then drops off dramatically. The delta 13 record. So here's -24. You come down here, shows an abundance of C3 vegetation, probably many more trees, probably hardwoods. There could have been in the very pre-10.7, that very end of the Pleistocene, there could have also been some pine based on pack rat middens that they've analyzed in the general area. There was pine in the area, but clearly based on the delta 13 values suggests more of a dominance of C3, and then you see it really drops off towards C4, getting up towards the -16, a little bit of an excursion back to C3, but then goes back to C4, and then this excursion to C3 is probably because of all the mesquite and the creosote that invaded the region. So the key here is, at least you see some patterns, a shift from C3 to mixed to C4, and becomes increasingly the trend going up is more of a C4, which tells you again, this is a signature of temperature. It's getting progressively warmer.
Dr. Mandel, sorry to interrupt, but I would appreciate it if you can wrap it up soon, because we are approaching 10. We'd like to have some time for Q&A.
Okay, I'm just about done.
Sure.
I'll I'm going to jump over to Calamity Creek. There's 3 sections I've looked at here. Here's section 1, which I'm going to zoom in on. You've seen this picture before. You've seen this one. There's my ladder. Climbed up, redefined the different units. Now as they originally had them as formations. These are now should be members. So there's the Calamity member, the Neville. You can see the carbonates in this paleosol, which is reddened. And if we look at the isotopes, it's a very similar pattern, very strong C3 at the bottom, and it does steadily shift towards C4 at the top. What's striking, though, is when you compare those 2 records, the Calamity Creek and the Neville. And so this, of course, matches with that. This matches with that. This matches with that. And this matches with that. So the 2 records are remarkably similar in terms of the isotope record. And that's, of course, what you hope to see. So what are the directions for future research? I want to do clustered isotope analysis on soil carbonates, like the O18, to hopefully maybe we can see about the different sources of moisture, Gulf versus Pacific moisture. Phytolith and pollen analysis, and particularly the latter at San Esteban Rock Shelter. The San Esteban Rock Shelter should have a really good pollen record. The phytoliths we can look at in many of these sections I showed you. Additional radiocarbon and OSL dating to assess the time transgression among the different members of the Likes formation. In other words, do they become progressively younger, significantly younger as you go up the drainage networks? And then to use a powerful tool, the Likes formation, as a guide and search for the earliest evidence of people in the Big Bend region. In other words, target the Neville formation for that search. And so to end, these guys actually got it right for the most part, without the, having, radiocarbon dating or isotope analysis. A lot of what they presented, other than the business with formations, we've just changed them to members, it was really remarkable. So kudos to them. And then finally, my last slide, I want to thank Bob Maloof, who used to be director of the Center for Big Bend Studies and still lives in Alpine and has held the ladder for me a lot as I was up on Calamity Creek section. Bryan Schroeder, who's the current director of the center, and Erica Blecha, who works at the center as well. They all really helped me a lot in the field. So I appreciate that assistance. And that is the end.
Thank you very much, Dr. Mandel, for your great talk. So far, I do not see any question in the chat box. So you are welcome to unmute your mic if you have any question, or you can easily write your question in the chat box. I will read the question for the speaker. And Michael, you are welcome to ask questions from the audience in the VR room, because so far I do not see any question.
When is he leading the field trip?
Okay, hi. What a great talk. Thank you very much. So you had mentioned that temperature is playing a factor in some of this, right? What do you have a sense of whether precipitation is changing?
That's the next thing we really need to look at, which I kind of rushed through at the end, talking about what we had to get at moisture. That's where phytoliths will become very helpful. The biogenic opal and the pollen will tell us more about moisture. You just can't use stable carbon isotopes to say any. I've seen people try to do it. My gut, I'm going to put myself out on a limb. I would say that when we go up into the Terlingua, remember that big thick cumulic A, that it was warmer, but it was also wetter. I think the water, I think the water table was up, which is why the organic matter is preserved. And that's exactly what we see with the Roberts Creek member in the Eastern Plains. Water tables were high then, which preserved the organic matter and of course facilitated its accumulation. And then on the opposite end, we look at like both the Calamity and the Neville, they're really oxidized, which says water tables were probably down. And of course, that's getting, at the end of the Neville, you're getting into the ultrathermal where it's, hot. It was probably hot and dry as you come out of the Pleistocene. So, but until we have a good pollen record, that'll tell us a lot more about precipitation, as will phytoliths. And of course, precipitation source from like 018 from the carbonates. So I'm really kind of in the early stages of that. I was hoping to be further along, but the pandemic kind of did us in on a lot of the analysis, to put it bluntly. But that, over the next few years, this is kind of, we're in the early stages of all this. This is going to be a long-term project. So we're going to invest heavily in this area in terms of doing science and answer questions like that. So it'll be fun, maybe in a few years to come back and tell you what the rest of the story. Yeah.
Okay.
Questions online?
Yeah, there is one question from Jenny Duncan asking, when will the Odyssey group come to dig at the GLD site this summer?
We'll be out there in the latter half of July and the first couple of weeks of August when it's really hot. The reason being, we're going to be over at San Esteban Rock Shelter through June. That's where we're going to look at that LUS record and the archaeological record at Harbors. But yeah, latter half of July, early part of August. People are, certainly welcome. We can arrange people who want to visit. It should be interesting.
So I don't know if there's time for one more question, but Rolfe, it's a great talk.
Thank you.
Fascinating sequence. And then one thing I was wondering about with the carbon isotopes, it looks like there might be an 8.2 Ka event.
Yes.
Excursion, which I'm sure you've already done.
Yes. Yeah, I at least suggest it.
Yeah.
Yeah. Which is kind of ubiquitous. I mean, you see that in a lot of places. So yes, quite possible we're going to detect that. And there again, it'll be really interesting when we look at the pollen record to see the bigger regional climate pattern. So, yeah.
There is not any more question in the chat box. So you're welcome to continue in the VR room.
Maybe I convinced everybody. Either that or I've confused everybody. Yeah.
Hey, Rolfe, that was a great talk. You referred to the silt in one of the units as LUS.
Right.
And
Well, what we see is a source of the LUS. Yeah.
Okay. So that was the question
Yes.
I was going to ask is, do you have thoughts as to where the LUS is being generated?
Yeah.
Is it all local?
I think a lot of it is. The top of the Neville is that, that reddish brown, really silty sediment, which, as I said, that Bryan and Albritton noticed that it was real silty, and they noticed that in the rock shelters there's this reddish brown silt that looks just like the Neville. They said that's probably the source, and I think they're right. That could very well be the source. In other words, you get these big broad floodplains, across those valleys, and the wind sweeping across it, picking up that silty sediment. There's an erosional surface, we know that, and then moving it against the valley wall, and it accumulates in the rock shelters. And so, we think the link there is, between the rock shelters, and that was the former floodplain, back very early Holocene, that it's a local source. I think that's quite likely.
Thank you.
And we're gonna fingerprint it and see if that's true.
So there is not any other question in the chat box.
Yeah, we are also good here.
Okay,
Yeah.
perfect. Thank you very much, Dr. Mandel, for your great talk, for your time and joining us today. And thank you everyone for joining us. Hope to see you all next week.
Thank you for having me again.
It was a pleasure.